Hello everyone, welcome to E407 Introduction to Control Engineering. I do apologize that this is the first video you're getting officially from me. I should have sent this out a long time ago. Having said that, here we are and we're starting. I'd like to start the course really by playing a video, and this is something you have undoubtedly seen at some point in time in your lifetime. You definitely have seen it before, but maybe you haven't taken it to heart. So let me start by playing this video. Just watch this.
Hey, it's me, Destin. I got my dad a present for Father's Day, and it's kind of weird. So I figured I'd show you an interesting principle with the present. It's a chicken. I got my dad a chicken for Father's Day, and I want to show you a pretty interesting method that chickens have to keep their head stable. You know, in guidance and control, you have feedback loops, and so you have to know your position and where your relative motion is going so you can compensate for it. But chickens are really good at this, so I'll show you. Watch his head stay totally stationary as I move his body. I can move his body in pretty much any direction, and his head stays rock solid in one position. This is really hard to do. So anyway, he knows exactly where his body is and where his body's moving. It's kind of fun to watch, isn't it? So they're really good at it. I don't really know why, but I'm sure there's an explanation. There's my sister Brawley with the other chicken. We got Dad, so anyway.
Mine has tail tricks. Up, down, up, down.
Look how solid his head is. That's kind of stupid. He'll probably pick me in the eyes, so I'll stop now. Alright, so bye.
Yeah, so simple video of a chicken keeping his head stable. And what does that have to do with E407? Now, he mentioned something. He mentioned guidance and control, and he mentioned feedback loops. Feedback loops is something we'll come back and talk about. We'll talk about it a lot in this course, and it honestly is a fundamental to this course. It's not a big deal, but I hope you saw in that video how steady the head of the chicken was. It's interesting that they're able to keep their head steady even though their body is moving up and down. To be honest, I think we have a lot we can learn from chicken if possible. Okay, next I want to play another video. And this is a video of a trash can. The person is speaking in Japanese, so I may just go ahead and be talking while the
engineer at a Japanese automaker won an Excellence Award at the Japan Media Arts Festival.
Okay, so what you see in here is a Japanese guy he's pointing to a sensor on the wall, and the fact that when he throws the trash can moves of his own volition and goes ahead to catch the trash. Okay, so the trash can moves to catch the trash. That's the second video. I want to show a third video. And in this video, what you will see is a slightly different system. I call it a slightly different system, but let me go ahead and just play it. So this is bowling, and then the whole idea is to try to get a strike in bowling. If you don't know what a strike is when you knock down all the pins, all the bowling pins with your ball. You roll the ball, and then if it knocks down all the pins, then that's called a strike. So if you want to be able to get a strike all the time, then you probably want to use the bowling ball that this guy, Mark Rober, will introduce. By the way, I want to mention at this point that each of these videos that you have that I'm playing, I'll give you the links to their videos, and I will recommend you go watch the entire videos. In many cases, I'm just showing you a portion of the video, not the entire video itself. The first video was by Destin Sandlin. The second video, I honestly don't know the name of the guy. The third video I'll show you now is by Mark Rober, and here's the video.
This bowling ball can get you a strike every time because after you bowl it, you simply lean in the direction you want the ball to turn. This idea has been on my bucket list for over 3 years, so today I'm going to tell you how we made it, how exactly it works, and what happens when you take it bowling, but neglect to tell the people you're bowling with about your slight advantage. So this trick ball looks and feels like a normal bowling ball, and that's because it's made
from a normal bowling ball. Let me just finish that statement for him. Okay, so it's actually made from a normal bowling ball, but they put some electronics on the inside. If you watch that video, if you want, you could just rewind this video and watch again and see that they basically hollowed out a bowling ball and put some electronics on the inside. Again, watch the entire video by Mark Rober. I want to specifically recommend that you subscribe to Mark Rober, actually. Subscribe to him and watch his videos. He comes up with interesting engineering stuff, and I really do recommend his channel. Destin Sandlin is also another person I watch a lot. The name of his channel is Smarter Every Day. Now, both of them have very great channels and they're doing interesting stuff. But what does all of this have to do with our course in the first place? Now, you had a chicken whose head was kept in one position, and somehow the chicken is able to keep its head in one position such that it simply tells its head, I want you to be in this position. And no matter how the body is moving, the head stays in that position. So you have a target, or if you want, you have an instruction you give to it, and you tell it, okay, this is a set point. So set point is another word that maybe you want to keep, or if you want another terminology that you want to keep. Sorry, I'm trying to get my pen to write over here. It's refusing to write. Okay, so set point is something that we want to keep in our repertoire of, if you want, terminologies, set points. So we have a set point, we specify the set point, set that into a system, we tell the system, okay, system, this is your set point, this is what I want you to do. Once you have done that, then then the system now responds. So how the system, whether the system actually obeys you and gets to the set point or not, is something we probably want to worry about a little bit. With the chicken, somehow it's able to get its head to stay in that particular position unless the body goes out of a certain boundary. So if the body moves outside a certain boundary, there's no way it can extend its neck or contract its neck to keep the head in that location, and the head will have to move. Okay, so that's just an interesting concept. So let's now apply that concept to the concept of bowling. He rolls the ball. Set point is, I want a strike. Rolls the ball, and while that is going on, he's watching to see, okay, am I about to get a strike? Am I going to get a strike? Am I going to get a strike? Am I going to get a strike? Based on that, he is now leaning left or leaning right. Leaning left or leaning right. And the whole idea is to make sure that the ball actually gets to the position and hits, if you want, your set points, hits the target. You can imagine the trash can. That is exactly what was going on over there as well. The trash is flying through the air, and before it lands, the trash can tries to figure out where is this trash going to land, and based on that, it moves to that location. All of this I just mentioned, really, they make use of what are called feedback loops. Okay, feedback loops. They make use of that. The whole idea is this: with the bowling, the particular reason why I showed the bowling video is that in that case, the human being is a part of the system. So the human being is watching. And based on what you can see, you are leaning left or leaning right. Now, I can as well tell you that there's an accelerometer or a gyroscope on his body, and that is so that it can sense the motion of the body, and based on that, it is transmitting it wirelessly to the bowling ball, and the motor inside the bowling ball is rotating something, and then that is causing the bowling ball to move left or right. But all of that you probably figured out already. Now, he is part of the system. He is serving as the feedback loop. He is monitoring what the ball is doing, and he is moving his body left or right to try to make sure that it actually hits the target. Let me play a fourth video and try to figure out the feedback loop in this case. Now, in this case, what you have is a dartboard. And again, this video is by Mark Rober. He made a dartboard to get a bull's eye all the time. In other words, whenever you throw the dart, it lands in the center of the board. Watch this.
I suck at darts, but I'm good at engineering, which means I'm actually really good at darts.
I want to just pause at this point, and I hope you heard that. I suck at that, but I'm really good at engineering. In other words, I am really good at darts. That's a phrase I think it could make a lot of sense if you just keep in your mind, and you always use it, keep it in your repertoire all the time if possible. That whatever it is you're not good at, you can actually engineer a solution. And think of Nigeria. Nigeria has a problem with whatever it is. We can create solutions for it because that is who we are. We are engineers. Engineers are problem solvers. Engineers are people who see issues, who see problems and find solutions to them. They find ways of ensuring that they find a solution. They find ways of ensuring they have a solution. That sounds like tautology to me. They find solutions to problems. That is who engineers are. Let me go ahead and play the video. I'll start it again from the beginning so you can enjoy it at least to the point where I'll play it.
I suck at darts, but I'm good at engineering, which means I suck at darts, but I'm good at engineering, which means I'm actually really good at darts.
Okay, so that's the fourth video, and we'll have just one more video that we'll go through sometime before the end of this lecture. So that is what we have, and those are 4 videos, and they all talk about control engineering. I think it's probably clear at this point that you know that I'm showing you systems that make use of control engineering. The chicken, it has an interesting control engineering system inside of him, and it's basically controlling the position of the head. You had the control of a dartboard to make sure that the dart will always hit the bullseye. You had the control of a bowling ball to make sure that it always knocks down all the pins. We had the control of a trash can to make sure that that it always catches the trash. Now, looking at all the systems, what you really just have in there is, I mentioned that you have a set point. If you want, the set point is a command that you give to a system. So you have a system. The system, if you want, is whatever it is that we are controlling. So for example, in some of the cases, we had the chicken head, if you want, being the system, or you had the trash can being the system, or you had the dartboard being the system, or you had the bowling ball being the system. So the system is what you are controlling. And then what you do is you give it what we call a set point. Okay, so you give it a set point. The set point comes in as the input, and then you have a certain output from your system. Okay, so you have an input, you have your output. Your output, if you want, should match. Our desire is that your output will exactly match your input. In other words, if I give it a command, it does exactly what I tell it to do. If I tell it move to position X, then when I check this position, it will always be X. Now, I could just leave this system like this. For example, I take a regular bowling ball and just roll the ball down. If I roll the ball down, it may knock down all the pins. It may not lock down all the pins. This is called an open loop system. Let's see if I can get my pen to write. Okay, so it's an open loop system. This is an open loop system. An open loop system is a system that does not have any feedback. It's a system where the inputs, there is no link between the output and the input. If you want, the input is not monitoring the output. Okay, so that is an open loop system. If you just roll a bowling pin down the alleyway and just send it to knock down the pins, all you can do after the ball has left your hand, you have supplied your set points. Once it has left your hand, it goes. Whether it knocks down all the pins or not is dependent on whether your set point was actually perfectly correct. Now, what if your set point was actually accurate? You're the best bowler in the world, but somewhere along the line on the alleyway, while it is going down the track, there's a little water, just a little water, or there is a bug that is there, literally a bug, a beetle or something that is there. When the ball is going, it now knocks it off the track just a little bit. What happens? It will not hit the set point no matter what. So no matter how great your input is, it always tends to happen that somehow you have some disturbance that comes in. So we could go ahead and try to model that in our system, that instead of just being able to supply a set point, sometimes you have something here that adds to the signal, and that is a disturbance. So now let me put in another command over here. And now actually I'll modify this system because this system is actually quite terrible. Now, so this is actually your command that came, but somewhere along the line, maybe some disturbance came in or some noise came in or something, and that is actually what gets to your system. Problem is you may not always hit your targets. You may not always hit your target. Now, that is the reason why we have what is called feedback control. Okay, that's why you have what is called feedback control. So let me draw this a little more accurately. Usually when we talk about disturbance, we don't put the disturbance at the inputs, because if the disturbance were at the input, generally it is quite easy to control. Now, I was trying to be a little lazy, but then it doesn't make any sense. I can't be lazy in here. So what I'm going to have to do is draw this correctly. So instead of having trying to have a feedback at the input, actually what the disturbance at the input, your disturbance usually gets added at some point in time, either to the output or somewhere in the middle, so that you could break the system into two, and somewhere in the middle you have the disturbance being added, so that it will probably have been accurate for me to draw the disturbance that's coming into the system. But usually we don't draw block diagrams that way. We usually don't draw more than one input going into a block. So because of that, I wouldn't draw it that way. Rather, I say that our disturbance adds to the output in this case. Now, what we want to do is to go ahead and take this output, monitor it, and send it back to the input. So if you want, you could think of this as your eyes seeing what the output is, what is going on at the output, and based on that, you're now modifying what is going on the input. This is what the chicken is doing, and doing very, very, very well. Chicken is doing it very, very well. The chicken actually is looking, or it's if you want, sensing on the inside of its brain. It is able to sense where is my head, and based on that, it now determines, okay, neck contract or neck don't contract or anything. So I'm supplying my set points to I'm supplying my set point to my system, and then I am monitoring the output, and both signals are getting added up. Now, this is typically a summer, okay? If you want, the two signals are getting added up. I know I'm not explaining a lot right now. Some things here might be cryptic. Just bear with me. You will understand it as time goes on. So that many times what happens is one signal that comes from here, we sum it with a signal that comes from here. Actually, usually we subtract it. So we have something called negative feedback. Again, what does that mean? Not so important at this point. What matters is you have an input signal, which is your set point. You have an output signal, which is your feedback that is coming in here. And then we now send something actually into our system. That is, if you want, this minus that. So, say for example, you say head, I want you to stay at position 2 meters. You check the output. What's the position? Position is 1.5 meters. What's the difference? 0.5. Then your signal that comes in here, we often call that our error signal. And that error signal, let's see if I can actually write ERR. Okay, so our error signal goes into the plant, and that error signal tells it, okay, you are 0.5 meters off from it. 2 meters is the set point, 1.5 is the feedback, then you're 0.5 meters off, moved by 0.5 meters, so it moves by 0.5 meters. So now the input that is coming into this plant is no longer the set point you are supplying, but is rather your error signal that comes after checking the feedback. So now what happens if the head is actually at 2 meters? 2 meters is our set point. 2 meters come from the feedback. Subtract them, what you get? 0. You tell the head, move by 0. What does that mean? It doesn't move and it remains. Now, if some disturbance of some sort comes in here and moves the head away so that the head is now 1.8, then you have that difference and it says move by 0.2 meters and it moves, despite the fact that you have a disturbance over there. Now, this is what is called a feedback system. And generally speaking, this is all that we'll do in this course. Okay, no, that's not entirely true. This is the whole concept of the course, okay? This is the whole concept of the course. When you want to control a system, generally speaking, we use a feedback loop. We subtract the feedback from our input and from our set point and send in our error signal into the plant. Now, let me just mention a couple of things. The fact that actually usually we don't send the error signal directly to the plant. Usually we have something that is in here that we call a controller. In some cases, we also put something in here that might be a gain for the feedback loop, or it might be the controller in its own case. In some other cases, we might need to have a gain on this other side, or in some cases, we may need to have another system over here. Then the question is this: how do we model all the systems? How do we model a chicken head? Oh, okay, no, let's come back to something more easier. How do we model a dartboard? How do we model all of this? So what's the mathematical equation between that? So we have to have the mathematical equation of this plant system. Then we have to understand also how do we get our, well, so we'll talk electrical signals. What type of electrical signal do I use to encode my set point? Then when I measure this, okay, what type of instrumentation system should be used here? By the way, we won't deal with that in this course. But then instrumentation is used to monitor what is going on at the output. You did that in 310. You will encounter that in 523 as well and co. But what kind of instrumentation system do I want to use here? What type of signal will it send back? So that the idea is this: you have a set point, an electrical signal. Your feedback is also an electrical signal. How do they interact over here? Then what type of error signal do I send? Now that error signal I send may not necessarily be exactly 0.2 meters or something. So what type of error signal, what kind of electrical signal is it? So maybe I need to put in a controller or an amplifier or something over here as a controller, and that controller will end up modifying the signal and sending it into the plant. The whole point is this. All of this is what control engineers do. And if you want, our work is quite easy. Arguably, obviously. Now, I want to mention that control goes way beyond elect-elect, goes way beyond elect-elect and mechanical. So if you look at the systems I showed you, most of them were actually electromechanical systems. But it goes beyond that. Imagine that you looked at the financial markets. And in the financial markets, because there was a war somewhere or something, there was a coronavirus, all of a sudden you get the stock market is falling, it's in free fall, and prices are just going bonkers and cool. You have a disturbance that has come into your system. That disturbance that's come into your system is making the outputs messed up. So you probably want to introduce a feedback loop and have a controller of some sort that will end up maybe being a stimulus or something. And the whole idea is to make the economy become what we want it to be once again. That's an example of where you can use a control system once again. I mean, control systems are used in several scenarios, so that understand that control engineering really is a lot about mathematics, understanding mathematical models, manipulating the mathematical models, and arriving at a solution that we're interested in. The whole idea is we effectively have a set point, and we now monitor the outputs through a feedback loop where at a controller we're able to make sure that the output becomes what we want. In fairness, we can't always do this. So if you watch the dartboard video by Makroba, he mentioned that once the output, once the dart, as long as you throw the dart generally, and it is going to land without help from him, if it is going to land within a certain range, then he can move the dartboard to actually intercept the dart and make sure it's a bullseye. If the if the dartboard is moving outside of a certain range, the dartboard will not be able to move far enough or fast enough to be able to catch the dart and to arrive at a bullseye. Same thing with the trash can. If the trash was not going to land, if the trash was, if you want, too far away from the set point, then that becomes a problem. Okay, and this is something we actually encounter in a number of systems. You find out that it might not always be possible to control a system. It might not always be possible to arrive at a particular output that we are interested in. However, what we try to do is, in some cases, if it's impossible to arrive at the particular output, how can we best get to something that we like? Can we actually arrive at this, at what we want, at something close to it, at what is the next best thing? So those are things we try to do as control engineers. I promised one last video, and now let me show one last video. This last video is by Bose. Bose, you know them as people who make headsets. And yeah, let me just go ahead and play the video. Let me not say too much about it. So here's the video.
We'll bring the cars down one after the other at a fairly slow clip. And I just want...
Okay, sorry, wrong video. Let me play this one instead. That video I could give to you as well, but this video is better.
You may know us as an audio company, but our technologies also play key roles in the aviation, nuclear power, and biomedical industries. And now, after 25 years of research, we have developed a new approach to automobile suspensions. The Bose Suspension System delivers greater comfort and greater control for a much smoother ride than any luxury sedan, with less roll and pitch than any sports car. This system uses proprietary software, linear electromagnetic motors, and power amplifiers to control each wheel. The following performance comparisons let you see the difference between conventional suspensions and the Bose Suspension System. Greater comfort and greater control simultaneously. The Bose Suspension System.
So I'll go ahead and just say that, take note that that video was done in 2004, okay? So 2004, yeah, a lot of things have changed in the automotive world since then. And this system, I should mention, was actually a commercial failure. The suspension system they came up with, it was too heavy and too expensive. So it was commercial failure. However, that technology was moved into seats. That's chairs that are used in the car seats that are used inside trucks to make them very comfortable inside trucks, okay? So it was a commercial failure, but really that is why we do engineering. I hope you could see how flat the car was compared to other cars. And now you probably understand why some cars are more expensive than others, why some cars are more comfortable than others. But how does the suspension work? You have a set point, you have a feedback, you have a controller, and that's all about it. See you in the next video.